So, now you should get one of those and the free response questions. Anybody see the free response questions? Right there. Yep. You probably have that already. You need that. And the free response question. Those two are sufficient. All right, so how's the diagrams? Any questions on the free body diagrams? Yeah, sure. Which one? Pick one. Don't say all of them. Pick a couple. Yes. Oh, springs, don't worry about. Springs we'll get to. That's going to be a couple units from now. Okay, so number 14. So you take something like number 14. And I guess it looks like this. And there's like a string like this. And then there's a string like this. Is that it? All right. FT1, FT2, FG. There you go. That's it. Just remember, what you do with free body diagrams is you put yourself in place of that box. And you ask, what would you feel? And what would you feel? You would feel that pulling you that way, that pulling you that way, and you would feel the earth pulling you down. Anyone else? Come on, guys. There's got to be a couple more. Yes.
30.
Oh, 30. You are a bold man. 30. A block is placed on a rough incline. So you have a block. Okay, 150, maybe 100. Okay, so I'm going to call this body 1. This body 2. And this body 3. Meaning the floor is 3. Notice by doing this, what am I really doing? Allowing myself to be able to write 1 on 2, 2 on 3, and so on and so forth. So we have force of gravity. We have Fn of 2 on 3. Excuse me, 2 on 1. And we have friction of which body on which body? Yes? 2 on 1. Okay? Now we go to body 2. What are the forces on body 2? Gravity. So we have Fg. What else? Fn of 3 on 2. What else? Stay focused, ladies in the middle row. What else? Yes. Normal force of 1 on 2. And where's that directed? Down. Fn of 1 on 2. Notice it's equal and opposite to Fn of 2 on 1. And then you have, oh, you can't see that, can you? Yeah, kill the lights. And don't be afraid to come up here, all of you. Because you know what? You can't do this yet, and that's fine. But it's important to see how all these interactions happen. What else? What other forces do you have? Yes? Friction of 3 on 2. Let me see if I can put this in black. Maybe I'll improve it. The friction of 3 on 2. And where's, so now we have to think about where is this plane heading? Plane's moving this way because this thing is pushing on the plane this way, which sends it accelerating this way. So therefore, the force of friction from the ground on this plane is that way. So this is F friction of 3 on 2. Anything else? I think that is almost it. There's only one more force. Anybody see what it is? It's the force of friction of 1 on 2. And where's the force of friction of 1 on 2 directed? Opposite direction of 2 on 1. So it's like directed downward. This is force of friction of 1 on 2. It's tough. This is tough stuff to actually diagram out something as complicated as a block moving on an inclined plane like this. To do it for each body. Which is why in first year courses, what do? They take the inclined plane and they bolt it to the ground. So now it becomes much more simple. Other questions? You sure? How many of you guys actually gave a solid, legit effort on the free body diagramming? Okay. And how solid was that effort? How many people put in more than an hour? No, that of course not. I mean, you think some of those problems are like, what are the forces acting on it? Yeah, actually, if you need more, come and get them. I actually have many more. Don't be afraid to get them. Because the time you spend now is time that you will save later. This is the unit. Talk to anyone that's a senior this year who had my class last year. They will say, forces, forces, forces. So, all right, now, let's see. Pear deck or go deeper into the course? Let's do pear deck first. Let's see where you guys are at with forces. From this class? That was a joke. Oh, wait. Let me see. Go to switch views. Invite you guys. Actually, you know what? I don't think I've updated the class for... All right, guys. Here we go. A book is lying at rest on a table. The book will remain there because yeah, I didn't even invite the class. It's FNBPP because I have to change my Google Classroom to account for the fallen. As I like to call them. "30 seconds, guys." What? Yes. Correct. Normal force, gravity. That's it. All right. So, time. And what do we have? 4 is correct. There's no force on the book. That's why it's at rest. A hockey puck slides on ice at a constant velocity. What is the net force acting on the puck? 15 seconds. 5 seconds. It's totally obvious. Constant velocity means net force is 0. That's right. Net force equals 0 means the object's moving at a constant velocity. Don't get tricked up by the fact that, you know, there's forces acting on it, right? What are the forces acting on the puck? Gravity and normal force, right? But the net force is the sum of those two, which is 0. Number 4 is correct. Let's see where you guys are. All right, 10 seconds. Andrew, Brian, Julia, Vincent. All right, you guys are 5, 4, 3, 2, time. Show you the responses. They're all over the place. All right. So the majority thinks the answer is C. And guess what? The answer is 2. No net force acted on the book. Why did the book slide off? What had a net force acting on it? The bus. The bus had a net force acting on it. The book remained at a constant velocity. As a result, it slides off the bus, or it slides off the seat. Notice, what is this related to? This is related to why it is necessary for you guys to wear your seatbelts on the bus. When you don't wear your seatbelts on the bus, what happens? The bus accelerates into your face. It's the truth. So what's the force that usually keeps the book on the seat? And you have to be a little careful because there's multiple answers to this question. What is the force that usually keeps the book on the seat? And the answer is, there is no force usually that keeps it on the seat. Why? Because usually the bus is at constant velocity. So then the question is, what is the force that keeps it when it's accelerating? And the answer is, you can feel it on your butt when you sit down. It's not the normal force. It is static friction. Very good. It's static friction. That's what you feel when you're turning corners. Notice you're feeling at the bottom of your butt as you're turning a corner. It's static friction that's putting a force on you. So, you kick a smooth stone on a frozen pond. The stone slides, slows down, and eventually stops. You conclude that All right, 10 seconds. And that is correct. The answer is 3. A net force acted on it all along. What would you have to do to keep the stone moving? You have to apply a constant force to overcome the force of friction. Yes? Yes, but they're telling you it slows down. So that means that clearly ice is not perfect. So consider a cart on a horizontal frictionless table. Once the cart is given a push and released, what will happen to the cart? 10 seconds. Read it closely, Brian. And released. All right, 5, 4, 3, 2, 1. Time. The answer is 4. Continues with a constant velocity. That's right. All right. We just decided that the car continues with a constant velocity. What would have to be done in order to continue for the car to... Whatever. I can't talk. What would you have to do to keep it at a constant acceleration? There you go. You push the cart continuously. That is correct. All right, truck on a frozen lake. Frozen is another word for frictionless. Frictionless. All right, a large truck sits on a frozen lake. Assume there's no friction between the tires and the ice. A fly suddenly smashes into the front window. What will happen to the truck? Yes. It says what will happen to the truck. Okay. So it looks like you guys got trolled. All right. When it says frictionless, it really means it. Frictionless means no friction, which means it's definitely 2.
So what about the inertia though?
Well, that just means the velocity is going to be incredibly small.
Oh, okay.
But it would be still moving back because frictionless means frictionless. Yes.
Would ice have static friction?
Well, if it was sliding, there would be kinetic friction. But since they say it's frictionless, there's no friction. So, what's the truck doing at 5 minutes after it gets hit? Same thing it was doing 2 minutes after it got hit. It's moving at a constant velocity. All right, now you got to get your hands dirty. From rest, we step on the gas of our Ferrari. Provide a force F for 4 seconds. Speeding it up to a speed V. If the applied force were cut in half, how long would it take to reach the same final speed? Don't overthink it.
I think it should be 2, but I feel like that's so obvious.
Don't overthink it.
I like a Can we hear it?
No. Unfortunately, no. All right. So, what do you guys have? What do you have? What are you doing to the acceleration? Cutting it in half. In order to reach the same final speed, you'd need to double the time. V equals AT, assuming that VI is 0. V equals AT, you'd have to double the time to reach the same VF. So, now you need to actually really get your hands dirty. From rest, we step on the gas of our Ferrari, provide a force F for 4 seconds. During this time, it moves 50 meters. If the same force were applied for 8 seconds, how much would the car have traveled during this time?
8 times 4 is 30. It's constant velocity.
Think what same force means. Why? What is this? Why? Because what is the same? The mass is the same. So same force, same mass, same acceleration. So same acceleration, and you've done what to the time? Double the time. What's going to happen to the distance? Don't forget your kinematics. X equals 1/2 AT squared, which is 1/2 F over M T squared. Delta X is equal to 1/2 A T squared, but A is equal to F over M. So it's 1/2 F over M T squared. Notice you double the time. What's going to happen to displacement? Quadruple. So there you have it. Why is there no V0T term? Because from rest, we step on the gas of our Ferrari, and we go, what, 40 meters? Up to a final speed of 50 kilometers per hour. If the same force would be applied for 80 meters, what final speed would be reached? This you're definitely going to have to get your hands dirty for. I wouldn't, no, you're not going to be able to do it that fast. Get cranking away, guys. You have to be able to answer these quickly. 10 seconds. Five. Gotta move fast, guys. Yeah, proportions is an issue. All right, I'm going to call time. All right, looking at this, what's our operative equation? Second kinematic, Vf squared equals 2a delta x. Notice, why did I not include Vi? It's 0. So, we have Vf2 squared equals, notice, what's A? A is just simply F over M. So it's 2F over M delta x2. Vf1 squared is equal to 2F over M delta x1. Guess what I'm going to do with these two? Divide them. Boom, boom. What's delta x2? 80. What's delta x1? 40. Notice what happens to these two? Cancel. So, this is equal to 2, and that's equal to V2 over V1 squared. So therefore, V2 is equal to root 2 V1. What's V1? Yes? 50. What's the square root of 2 times 50? Square root of 2 times 50? Square root of 2 times, it's 70. It's 1.4 times 50 roughly. Questions? You're going to need to actually work faster, and you're going to need to have these equations down and know when to use them. All right. So, all right, with this, I want to actually go back and start moving forward. Because there's a bunch that we have to do that's left over for the other laws, but I would also like to start getting to problem solving. So, the first force that we're going to really start investigating is that of tension and the normal force. So, in order to actually really investigate it, I need to ask you guys, how do you measure your weight? And the answer is it's not so easy. So, what I'm going to tell you right now is something that's going to come strange to you, but it's a very easy way to lose weight. No, on Earth. On Earth. And so here's your scale. Okay? What your scale measures is the normal force. It is the force that the scale is exerting on your feet. That is what your scale measures. It measures the force that the scale exerts on my feet. So let's actually do this exercise. So we start off, and you're going to learn actually how to solve physics problems. So I'm going to throw the wool over your eyes before I do that, and I'm going to tell you right now, inertial mass and gravitational mass are identical. Period. So, what does that mean? That means I should probably tell you what weight is. Weight is also called the force of gravity. And it is equal to mg, where m is m sub capital G. That is the gravitational mass of an object. What is the gravitational mass of an object? Anyone? It is not the inertial mass by definition. I'm asking, what is the definition of the gravitational mass of an object? And the definition of the gravitational mass of an object, because I don't think I went through this with you guys. Did I go through this with you guys? All right. So the distinction between inertial mass and gravitational mass. Inertial mass is what? The resistance of an object to what? Yes. To a constant force. It's a resistance of an object to accelerate under a constant force. The gravitational mass of an object is the amount of force that an object exerts on another body of mass. Are those two the same? Inertial mass and gravitational mass? Like definitionally? No. Are they measured the same way? No. In fact, the actual measurement of gravitational mass is a little strange thing. I said before you put it on a scale. Well, what you're going to find out is that that's not actually measuring the gravitational mass per se. It depends upon whether your scale is accelerating or not. That's right. It depends upon whether your scale is accelerating. Well, you take elevators and you don't bring a scale with you? Well, you should start. Because everywhere you go, you should bring a scale. Just in case you happen to be accelerating. You want to see what the reading is. So right now, I'm going to actually tell you. Inertial mass and gravitational mass are the same. Mi equals mg. But they're not the same thing. They equal the same amount. But they're not the same thing. So I'm going to throw the wool over your eyes. And I'm going to start by showing you how to actually do a derivation. How to solve a forces problem. Yes? We do not know why. But what we do know is that the consequence of them being equal is actually very far-reaching in physics. And it literally goes down to the modern description of gravity itself, laid out by Albert Einstein. But why they are equal is not understood, and it's just considered a postulate. Yes? Yes. Everywhere. All right, so now, right now you guys learn how to do free body diagrams, correct? Now you need to learn where to use the free body diagrams. And the answer is you use the free body diagrams in Newton's second law. So let's deal with the simplest case. Simplest case would be a body in free fall. So an egg in free fall. What is the force acting on it? Gravity, right? And where's gravity acting? Down. So Fg. Then we write Newton's second law. And Newton's second law says what? The net force is equal to mass times the acceleration. And now we need to figure out what we're going to call up and what we're going to call down. What direction do you want to call up? Positive. So let's call up positive, and we'll call down negative. The free body diagram goes on the left side of Newton's second law. This goes here. So, what do you have? What is the net force? What are the forces acting on this body? What's the body? The egg. What are the forces acting on the egg? Gravity. Which direction does it act? Down. And what is down? So therefore it is negative Fg. No, that is not the simplest case. Negative Fg is equal to m times a. But what is a equal to? Negative g.
Please pardon the interruption for several announcements. There'll be no freshman girls soccer practice today.
So therefore,
2 tennis matches, varsity
Fg equals
the varsity plays their state match tomorrow at
Mg.
Summit. Also today, staff and students, please move their cars to the lower lot today. We have Del Barton at 3 levels of soccer, as
Next.
well as JV football. And
Book.
we need those spots. I really appreciate the help. Thank you.
On a flat table. What are the forces on the book? Gravity and normal force. Write out Newton's second law in every direction. Net F equals ma. Well, which direction is Fn? Up. So it's positive. And which direction is Fg? Negative. So you have Fn plus negative Fg. And that's equal to ma. But what's A? A is 0. So therefore, Fn equals which means Fn equals
Senior nightclub and homecoming tickets will be for sale in the gym for the rest of the week.
Fg, which equals nope, Mg. Focus. Fn equals Fg equals Mg because Fg is Mg. Going to be doing a lot of algebra this unit. If you weren't good at it before, you'll be good by the end of this unit. So, notice what we really just answered is you put a book on a scale. What are the forces on the book? Gravity and normal force. Right? Notice net force is Fn plus negative Fg. Is it accelerating? No. So that's 0. Fn equals Fg, which tells you that the scale gives you the weight. When you guys get back on Wednesday, which is a lab day, I'm probably going to go straight into lecture, and then we'll have lab later. Is it a lab day? Yeah. By the end of Wednesday, you'll be able to start doing problems.